Hi everyone. So this video is continuing on from the week 13 lecture where I looked at exam 2016 question 4, the Bode plot question. So if you weren't at the lecture, I recommend you definitely watch the Echo 360 video of that lecture first. I'm just going to continue from there. So basically at the end of that lecture, well, we were looking at this Bode plot question, and by the end of that lecture we'd sketched the Bode plot, which you can see here, and we'd estimated the gain and the phase margin from that Bode plot. So remember, from a Bode plot we can see that a system might go unstable by looking at the possibility a system can go unstable if it hits 0 dB and a phase of 180 degrees. So that combination of 0 dB, which is a gain of 1, 0 dB and 180 or any odd multiple of that, so minus 180, minus 360 and so on. So these are the situations that can cause instability, and the gain and phase margin tell us how far we are away from that. So the phase margin, we look at one of those conditions, we say 0 dB is satisfied, and we see how far away are we on the phase plot from being at minus 180. So that's the margin of error in terms of our phase estimate, phase response estimate. That tells us how wrong could that be before the system could go unstable. And looking at this sketch, I estimated that to be about 55 degrees. Okay, so this is minus 90, this is minus 180. So that's a rough estimate from looking at this sketch, which seems reasonable. So each one of these divisions is 90 degrees, so halfway would be 45. This is a bit longer than halfway, maybe it's 50, 55. The gain margin is kind of the reverse, so you look at the point where the phase crosses minus 180, and here it was significant that the sketch of the kind of estimate of what the Bode plot really does is actually a bit different to the straight line asymptotes. The straight line asymptotes hit minus 180 first, but the sketch of what the true Bode plot does will kind of skate above that for a while and then really sharply decrease close to the natural frequency of those resonant poles. So we looked at that point just before 80, which was the natural frequency of the resonant poles, and then we look at how much would the gain have to increase before we hit 0. And I looked at that and I estimate that's about 100, 110, somewhere around there. I think I said 110. Within kind of an exam situation, anything kind of about 100 to 120, 130 would be fine. And of course, when you're studying at home, you can also look in MATLAB and you can sketch the Bode plot. So if we look at those two, the hand sketch and the MATLAB sketch, they're pretty similar. You can see that actually the true plot in MATLAB has an even sharper roll-off in phase than I sketched during the lecture, but that's a fairly minor difference. The spike here is also a little bit sharper, but that's also a relatively minor difference. And in MATLAB you can look at the gain and phase margins, and the gain margin here is exactly 102 and it's at frequency 72 radians per second. I estimated 70 radians per second at 110, but that's close enough for a hand sketch. The phase margin here was happening at 0.065. I estimated somewhere around 0.06, and it's a 56.8 degree phase margin, where I said something like 50 to 55. So again, that's fine for an exam situation with a hand sketch. Okay, so if we move on now, we've got those gain and phase margins. From there, it's a simple calculation to tell us, estimate an overshoot and do a calculation of how much gain would be required. So if we go into the final part, which unfortunately here is labeled C, but should have been D because of some labeling mix-up in Microsoft Word. So the objective here is to reduce the settling time to 10 seconds and achieve less than 20% overshoot. And we just started talking about this at the end of the lecture, but here we want to go through this design in complete detail. Then there's a couple of follow-up questions about the steady state errors. So we'll do the design first. So here, the first thing you should think about is what's the overall objective? There are two kind of broad objectives that we're looking at. One is sometimes we want to improve the steady state performance. Other times we want to improve the transient performance. So kind of the transient is what's happening in the short term, so things like rise time, settling time, overshoot, whereas steady state is the long-term behavior, so where does the system actually end up after the transient has finished. And so generally, if we were looking at steady state, we'd be looking at PI or lag control, which is approximate PI. But here we're looking at transient, so we're talking about settling times and overshoots, and so that means we're looking at PD or lead control. And I'll do a lead design here. You could also do a PD design, but the advantage of lead design is it allows us to very precisely specify the new phase margin that we want. Okay, so let's go back and we'll have a look now back at the lectures of Bode plot design. And so let's have a look at some of the characteristics that we want to satisfy here. So we want to, first of all, satisfy a settling time requirement and then satisfy an overshoot requirement. So as with all of these relationships between Bode plots and transient response, the relationships are a little bit fuzzy, a little bit approximate, but we can use some rules of thumb. So what we'll do here is we'll just use some rules of thumb to kind of give us a reasonable design. And then for a real system, or if you're doing this for an assignment, you'd probably tweak it from there. But for an exam situation, you can just stop after you've used the rules of thumb. Okay, so the first thing we want to understand is what's the relationship between the closed loop bandwidth of the system, so that's a frequency response specification for closed loop, and the settling time. And here, even for second order systems, that's a fairly complicated relationship depending on zeta. But for systems that we're looking at, we're probably going to have a damping factor somewhere, especially for 20% overshoot, is going to be more towards 0.5. If we want to come up with, let's say, a safe bound, so a bit of a conservative estimate for that, we can say that settling time is about 10 over omega BW. So really it's more likely somewhere between 5 and 10, but if we assume it's going to be 10 over omega BW and it ends up less than that, then we'll consider that to be okay. So we can say approximately here TS equals 10 over omega BW. Okay, now what's omega BW got to do with our Bode plot? Well, actually, the closed loop bandwidth is related to the open loop frequency response. So the open loop frequency response is what we're plotting in a Bode plot, right? So if we look at this is a Bode plot of the open loop system, whereas the bandwidth is a property of the closed loop system. So what's the relationship between them? Well, again, it's a little bit complicated to give it precisely, but roughly speaking, the closed loop bandwidth is pretty close to being equal to the open loop crossover frequency. So what is the closed loop bandwidth? It's the frequency at which the closed loop system is minus 3 dB. And here, for a bunch of different phases, that tells you what the open loop system should be at. So for phases up around here, the open loop system should be at 0 dB. So that's exactly the crossover frequency that we're looking at here, 0 dB. And maybe it's where it's a bit lower here. So depending on the phase, it might be when it goes down to minus 3, down to minus 6. So you're looking at somewhere in this region here. You can say without too much approximation, you can say that omega BW is approximately equal to omega C, where this is the crossover frequency, or the 0 dB frequency. and maybe, or you can say somewhere it's between omega c to twice omega c. And so again, if we assume that just omega BW equals omega C, again we're going to be getting a conservative estimate because settling time is divided by omega BW. So if we say settling time is approximately equal, again this is approximately equal to 10 over omega C, then the real settling time will probably be a bit quicker than that because it might be 10 over 2 omega C, or this might be 5 over omega BW. So we're probably expecting the true settling time to be somewhere maybe around half this value if we're lucky. Maybe if we're at the extreme ends of these limits, it's more like a quarter of this value. But this kind of gives us a reasonable upper limit on settling time. Okay, so if we assume settling time is approximately 10 over the crossover frequency, we can look back now at our Bode plot, and we say the crossover frequency here, somewhere in this region, it's close to 0.1, or the bandwidth might be around 0.1. So we're looking at about 100-second settling time here. We need to improve that to be about a factor of 10. Okay, so what do we need to do? We already started this on the lecture, so it's already filled in a little bit. We need to be improving our bandwidth, or improving our crossover frequency to be more like 1 radian per second. So if we want, so this is the approximate formula, we want the settling time to equal 10, so obviously that says that our omega c should be approximately equal to 1 radian per second. Now, how do we get a crossover of 1 radian per second? Well, we need to actually push up the this Bode plot, right? And so you remember that if we just adjust a gain, just adjust a proportional gain on the system, the proportional gain doesn't do anything to the phase response, right? A proportional gain doesn't change the phase response at all. This will stay the same. On the other hand, the magnitude response will just be pushed up or down. So a proportional gain, we're taking a complex number and we're multiplying it by some gain Kp. And then that's just going to scale, as long as Kp is positive, all that does is it makes the magnitude bigger or smaller. It doesn't change the angle of the complex number. I should mention, of course, this is Kp, but actually in decibels, right? So we could say in terms of the true Kp, we're going to push this plot up by actually 20 log 10 of Kp. So for Bode plot design, you're often going back and forth between decibels and gains. So here, if we have a look at this, what does Kp need to be in order to get us so that the 0 dB frequency is more like 1 radian per second? Look at that. It looks like, so this is minus 50. It's a bit above that. It looks like it's about here. This point here looks like it's about minus 40 dB. So if this is at minus 40 dB and we want to increase so that this at this frequency we're at 0 dB, that means we need Kp to give a boost of 40 dB. Okay, so what does that mean? We want 20 times log 10 of Kp to equal 40. And another way to write that is we can write that as Kp equals 10 to the power of 40 over 20. That's just reversing this formula, or taking Kp out of this formula, which of course is 10 squared, which is 100. Okay, so we've already done part of our gain. We've part of our controller. We've figured out a Kp so that we meet our bandwidth specifications. If we apply this Kp, then we shift up the Bode plot, and I started to kind of sketch that in the lecture. So the whole Bode plot would be just like the one before, but everything pushed up by 40 dB. Okay, so if we look at our specifications now, what we wanted to achieve was actually a settling time of 10 seconds, an overshoot of less than 20%. So we've chosen KP for the settling time specification, but that's probably going to do some damage to our overshoot. So we've got a new crossover frequency here. Then remember, the relationship between the Bode plot and overshoot is indicated by the phase margin, okay? And here the phase margin, if you change the gain in the system, you don't change the phase at all, but you do change the phase margin. The reason for that is the phase margin is this phase difference at the frequency where the gain is 0 dB. So by pushing the gain up, I've changed that frequency where we evaluate the phase margin, and now you can see here the phase margin is absolutely tiny. It's almost 0, okay? And so if we have a look back at our lecture slides, what's the relationship between phase margin and overshoot? Generally, the smaller phase margin we have, the larger the overshoot that we have. And so actually there's a relationship here. There's within the kind of up to about a phase margin of 70 degrees, there's an approximate formula that the damping factor is approximately phase margin divided by 100. And so if we look at this, this system, when we've got the gain up here, we've got the phase margin very small, then the damping factor is also going to be extremely small. And so what that means is, for a system with a very small damping factor, you're actually going to get lots and lots of oscillations, and it's going to actually take a very long time to settle. So we need to get rid of that. We need to reduce the overshoot so that we get increase the phase margin to reduce the overshoot. And if we wanted an overshoot of about 20%, then we needed a phase margin of, let's say, roughly speaking, close to, if we're being a bit conservative, close to 50 degrees. You could use 0.45, you could say 45 degrees to 50 degrees. That's kind of the region that we're looking at to satisfy our specifications. Okay, so how do we boost the phase margin? Well, that's exactly what the lead controller is for. So a lead controller has a Bode plot which looks like this. So the key point is that at some kind of central frequency that we choose, the phase is boosted, and the main idea in lead design is to choose at what frequency you want to boost the phase and how much you want to boost it by, and then there's a formula for setting what the lead parameters should be. We also notice from the Bode plot that actually that's also going to increase the gain. Remember, from Bode's gain-phase relationship, roughly speaking, the phase plot is the slope of the gain plot. And so if you want to have a boost in the phase plot, that's going to require a kind of a section of the gain plot where the gain is increasing. Okay? But unlike a PD controller, it doesn't keep increasing forever, it levels off at some point. Now, we need to take this boost into account a little bit to do some adjustments, but the main idea is to choose a frequency and to boost the phase at that frequency. So if we look at the procedure in the lecture slides for Bode design for lead compensators. So we've already done step 1, which is to find an open loop gain K to satisfy the steady state error or bandwidth requirements. So we looked at a bandwidth requirement for a settling time of 10 seconds, and we chose K equals 100 for that. We've evaluated the phase margin of the system using the value of the gain chosen above. So with that gain, the phase margin of the system went to almost nothing, okay? And so basically we're saying the phase margin is almost 0, so we need to really kind of boost the phase to whatever it is we need. So we need a phase lead of something like 45 to 50 to meet the overshoot of 20% requirement. I'm going to say let's have a phase boost of 50. Part of the reason for that is that it's good to include a little bit extra because of the change in the crossover frequency that we'll come to in just a moment. Okay, so once we've got a value for how much we want to boost the phase by, and I'm going to say let's boost the phase by 50, we work out a parameter alpha, which is 1 minus sine, and it's important that this is, for example, if you're using MATLAB and you're computing phi max in degrees, make sure that you use not SIN, but SIND. So SIND will compute sine with degrees. Okay, so if you've got alpha is 1 minus sine of 50 over 1 plus sine of 50, it turns out in this case alpha equals 1 minus sine 50 over 1 plus sine 50. That turns out to be 0.1325. Okay, so we've already got now one of our parameters for our controller. And then what we've got to do is we've got to take into account this thing that we mentioned before, that not only are we boosting the phase, but we're also boosting the gain. And what does that mean? That means that actually, so we've put in a KP to put the crossover frequency here. Actually, the crossover frequency is going to be a little bit higher because not only does the KP boost the gain, but the lead compensator boosts the gain a little bit as well. And so the crossover frequency is actually going to shift a little bit further to the right, which is generally okay. That probably means that actually we're going to further improve the settling time. But it does mean that the phase margin might get a little bit worse. And so that's why, as I mentioned before, instead of saying 45 degrees for phase margin, we put in a bit of kind of a slop value of 50 degrees. And it also means the frequency at which we want to boost the phase the most is probably not going to be at 1, but it's going to be a little bit higher, right? Perhaps somewhere over here. Okay, so it's we have a formula to work out where that will happen. Basically, we can tell that at the particular central frequency, so we want to choose some omega max to boost the frequency. It turns out that the gain, the magnitude, will actually increase by 1 over square root alpha. So alpha is generally going to be less than 1, so 1 over square root alpha will generally be larger than 1 for most lead designs. And again, log of alpha, if alpha is less than 1, this log of alpha will be a negative number, so minus 10 log of alpha will be a positive number. Why is it minus 10? Because you get the minus sign from the computing the log of 1 over something, and instead of minus 20 log of square root of alpha, the square root can kind of come out the front and becomes divide by 2 when you're taking a factor outside of a logarithm. So I've actually got minus 10 log alpha is the same as 20 log 10 of 1 over square root alpha. Okay, so what does this mean? This means this is going to be the amount, okay? And for this particular system, if I put the alpha that I computed in before, so if I put in here minus 10 log of alpha, what I compute here is actually 8.77, okay, for this value of alpha. And so what does that mean? That means that when I look back here, at whatever frequency that I choose to boost my phase by, the gain will actually, the magnitude will actually also go up by 8.77. So for this sketch here, it looks like it was 10, but for our particular value of alpha, the gain, the magnitude of that central frequency will go up by 8.77. Okay, so how do I use that in my Bode sketch? I look at this and I say, okay, here was my new, this is where I boosted the crossover frequency to. We're using just my gain. Okay, so using KP, the crossover frequency becomes moves up here. Now my lead controller is also going to boost the magnitude as well, and it's going to push the crossover frequency a little bit further. How do I know how much further? I look at where this sketch would have gone through minus 8.7, because it's going to boost my gain by a further 8.7 dB. And it's a little bit tricky to see on this sketch, but let's just estimate that as 1.5 because this is going down. So if we just try to sketch this in, it's a little bit hard to do by hand, but again, in an exam, if you can show that you're using the right process, then it's not going to matter if your sketch is a little bit off. Here, each of these dots is kind of minus 10, so minus 8.7 is coming in pretty early here. It could be anywhere between kind of 1.3 to 1.7 or something from the accuracy I can see on this sketch. But I'm just going to say it's 1.5 radians per second. So this is going to be my new crossover frequency with the combination of KP and the lead controller. So if this is my new crossover frequency, here of course the phase margin is also nothing, almost nothing. I'm going to boost that up by 50 degrees. Okay, so I want to have a lead controller that comes in and puts in a real kind of lump in the phase here. Okay, so how do I do that? Well, I've figured out my new omega max from this formula should be 1.5 radians per second. And so we've got another parameter for the lead controller, which is T. And we can use the fact here that omega max for a lead controller is 1 over T square root of alpha. So if we have here omega max equals 1 over T square root alpha, then we know alpha, we know omega max. Of course, we can then just say T equals 1 over omega max square root alpha. And for this particular system with this value of alpha and omega max equals 1.5 radians per second, I get here a value of T 1.83. Okay, and so now we're basically done. Now our lead controller is TS plus 1 over alpha TS plus 1. So we figured out alpha, we figured out T, and so that's it. So before we get to the final part of the question, which was about steady state error, what I want to do is actually just show you some MATLAB simulations, and I'll put the M file online that I used to generate this, so you can practice with other questions. So if we have a look in MATLAB, okay, so let's have a look in MATLAB. This is just setting up the problem. This is just going through all the same computations that I did on the whiteboard. So I've got set KP equal to 100 to meet the bandwidth specifications, set phi max to 50, so how much we want to boost phase by. Then that gives us a value of alpha. Then the gap here, well, I computed minus 10 log alpha, but you can do it either way. And so we go through here, that gave us a value of 8.77. Then the T value for the lead compensator is 1 over square root alpha times omega max, and that gave me 1.83. And then the lead compensator is just, so the lead part of it is TS plus 1 over alpha TS plus 1, and then you're multiplying that by KP. And so that's the lead compensator, and we'd be perfectly happy for you to write it either in this form, or you could write it in terms of an overall gain and a specification of a 0 and a pole. So if we have a look now, of course we've got the original Bode plot. So this is the original Bode plot of the original system, and this is the Bode plot of the lead compensator. So you can see that at 1.5 radians per second, which was the omega max that we specified, we've actually got a phase boost here of, it should be 50 degrees, and as you can see, 1.5 radians per second, exactly 50 degrees. Okay, and then the overall magnitude, we've got 40 dB from the KP. Okay, and then at 1.5 here, we were there we go. It was supposed to be a further 8.7 about from the lead compensator, and so that's 48.8. Yeah, so that's just rounding, so that's fine. And so this lead compensator is doing exactly what we thought it should. And so what happens when we put the two together? So if we make the loop transfer function, the loop is G times K lead, right? And then let's plot a few things here. So we can we can begin in the frequency domain. So I'll just bring all of these plots around. So I'm plotting a few things here. So this is the combination, actually, of the open loop system. So this is the loop, which is the controller times G. And so we can see it looks kind of similar. You've still got this peak here. But compared to the original system, the main thing is, well, on the one hand, if we bring back figure 1 here, on the one hand, we'll see a big boost in the gain, so that the crossover frequency is pushed up much further up here. Okay, so if we compare these two, this is the open loop system, this is the combination of the open loop system and the controller. So here the crossover frequency is pushed up to 1.5, which is exactly what we specified. And if we look at the phase response here, instead of going down to minus 180 here, the effect of the lead compensator has really come in here, and we've got quite a nice phase margin of more than 50 degrees. So we can actually have a look of around 50 degrees. If we look at the stability margins here, what's the actual phase margin? 54.1. Okay, so that's fantastic. That's what we wanted. So now we can have a look at some other plots. So here we go. So this is the step response of the system. So we wanted a settling time of 10 seconds and an overshoot of 20%. So if we look in the peak response, we've got an overshoot of 21.8. So for a first cut design, based on some approximation, some quite rough approximations from a sketch, that's perfectly fine. That's as close as we would ever expect. And if we look at settling time here, it's actually half the specification. So we specified 10 seconds, it's more like 5 seconds. And this is due to those somewhat approximate relationships, like settling time is 10 over closed loop bandwidth, and closed loop bandwidth is exactly equal to the crossover frequency, where I was estimating them at the more conservative end of the range of possible values, so that I would get a shorter settling time rather than a longer settling time. So getting 5 instead of 10 is perfectly fine in those terms as well. We can also have a look here at the closed loop transfer function. So if we look at the closed loop transfer function, what is the closed loop bandwidth? The closed loop bandwidth is where it passes minus 3 dB. And we were saying the closed loop bandwidth is going to be approximately equal to the open loop crossover frequency, or maybe a bit higher than that, maybe more like double that. And if we look here, the open loop crossover frequency was 1.5. The closed loop bandwidth is 2.3 about. So if I'm guessing that the closed loop bandwidth is somewhere between 1.5 and 3, then the true value of 2.3 is about right. And now, just for interest, if we're thinking about fundamental limitations, we can look at our sensitivity function. And we know that the sensitivity function should, in this case, since there are no open loop unstable poles. I mean, there's one integrator, but none in the strict right half plane. We know that this signal, this function, should actually integrate to 1. Now, if we look at this, it looks a little bit like it's not going to integrate to 1, meaning the area of the curve kind of below 0 and the area of the curve above 0 should be equal, but that's actually because we're plotting on a logarithmic scale. So this whole range here is the range from 0 to 1, and this range here is the range from 1 to 10. So this range here on a linear scale is actually 9 times bigger than this range here, and that's why this area can integrate to be the same as this area. And we can actually modify the sketch. So if we look at the frequencies on a linear scale rather than a log scale, we see that illustrated here. So we can zoom in on this region. And now you see much more clearly actually that there's a much longer range of frequencies where you're above 0, and the range where it's below 0 is actually very narrow. Okay, now if we look at the final part of the question, it was asking what would the steady state error be for a unit step input, and also the steady state error for a ramp input of unit slope. So let's go back to our transfer function, and I've written it out again here. Remember, when you're doing Bode plots, it's very nice to factor out all of the kind of constant terms out the front and write the rest of the transfer function so that all of the lowest order terms are just 1. The reason for this is there's a few things. One, it's for sketching the Bode plot, but also when you're looking at steady state values, you're often looking at what happens when s equals 0. And when s equals 0, this whole thing is just going to be 1, okay? Because all the terms that don't have a power of s are just 1. So we're going to have this part left over. Similarly for the lead compensator, we had some values of alpha and t here, but they're not going to matter when s equals 0, because when s equals 0, this just goes to 1, and we've just got the 100 out the front. And so if we think about what is the steady state error going to be to a unit step input, well, we can immediately see that this system is type 1, right? It's type 1 because there's a single integrator, and that means that for a unit step input, the steady state error is just going to be 0. Okay, this is just something you can state. Because there's an integrator in the loop, a single integrator in the loop, there's going to be 0 steady state error for a step input for the closed loop system. And we actually saw that on the previous, when we looked at the step response before. Now, type 1 means that for a ramp input, so this was for step, unit step, for a ramp input of unit slope, for a type 1 system, it will have a constant steady state error. We're going to have E steady state equals 1 over kV, where kV is the limit as s goes to 0 of s times g of s. Here the g is not actually the not just the original system. Actually, we should perhaps write L of s here, because we're looking for the steady state error for the combination of the controller and the original system. So it would actually be L, which is k times g. So the s here, this s is going to cancel this s, and if we're looking now as s goes to 0, then all of this becomes 1, all of this becomes 1. So actually we're just going to end up with kV equals 100 times 0.0781, which is of course equal to 7.81. And then if I compute the steady state error to just be 1 over that, in this case that is going to equal 0.128. So for a unit ramp input, the steady state response of the system, it will always be 0.128 behind the ramp. So we can actually now plot that in MATLAB. So if we plot in MATLAB the response to a ramp input, which you can actually do by just plotting a step, an integrated step, so step of 1 over s, Then if we look at this, at the moment they look like they're basically on top of each other. We've got a tiny transient at the beginning, but if we zoom in on some region like this, if we look in close to 100, and we look at this, oops, I zoomed in on slightly the wrong spot here, just to make it nice and clear. So this, the red line is the reference, and the blue line is the system response, okay? And the red line at 100, the reference of a unit ramp with unit slope passes through exactly 100, whereas we've predicted that this should be 0.128 below. This looks like it's about 99.872, which is exactly 100 minus 0.128. So in MATLAB, we've verified what the final value theorem tells us, that the steady state error to a unit ramp should be 0.128. Okay, so that's basically the end of this question. If you liked this video and you'd like to see more, then if you haven't already done so, please fill out the USS survey now. You can see there's a link on Ed, and you're probably getting various notification emails as well.